Let's see here. So, much like the things we have done this quarter have been sort of analogs of things we did in 17A or B, but just kind of like extending them, like with the linearizations with the tangent planes, how like that was just kind of like what we did with the linearizations in 17A, where we just kind of added on a dimension, or with like the finding the maxima and minima, kind of the same idea, except you're kind of adding on another piece. This is going to be kind of like that, in that we're going to be doing something similar to what we did in 17A, but we're kind of adding on another piece, which makes it a bit more complicated, but it's still the same idea. To that end, let's recall the idea from 17A, and then we'll kind of see what the picture looks like. So, or from 17B, I should say, sorry. So recall, hopefully in 17B, you saw a differential equation like this: dx dt equal to some constant times x, where a is a constant, x is your variable, your population, your function, whatever you want to call it, and t is time. And what this equation, I should say, what this differential equation says is that the rate of growth of x as a function of t is proportional to the population size, x of t. Which a lot of things that kind of makes sense. Like if we're talking about people, right? The more people you have, the faster the rate of growth is, because more people make more people faster. Or bugs or cells or lots of other, or like oh, I guess there's another one I'm thinking of that I can't think of now. Anyway, so we have solved differential equations like this. I'll remind you how it goes. So if you're solving this differential equation, we solve it by separating variables. So you separate variables, separate, I can spell, separate variables. So we bring our x's to the left, our t's to the right. We get 1 over x times dx equal to a times dt. We integrate both sides. You get the integral of 1 over x dx equal to the integral of a times dt. The integral of 1 over x is the natural log of the absolute value of x, but I'm going to ignore the absolute value because we don't really need to worry so much about it. On the right-hand side, the antiderivative of a constant, is a times t plus some c. If you're wondering why I didn't write plus c on both sides, I could have. I could have written like plus C1 over here and plus C2 over here, and then subtracted the C1 to the other side and just had a constant over here. So really, there are constants on both sides. We're just going to bring them all to the side we're not solving for. And then we're going to solve for x, so we're going to exponentiate both sides and say that e to the natural log of x is equal to e to the at plus c. And then we're going to rewrite this as x, or x of t, equal to, we're going to rewrite this as e to the at times e to the c. And then we're going to say that e to the c is just some other constant. We're also going to call it c, because who wants to use a new letter? We can reuse the same letter. So the point of this exercise was to remind you that when you're solving this sort of differential equation, specifically the differential equation where the rate of change is proportional to the population size, your solution is exponential growth. You get that your function is some e to the at times a constant. Exponential growth. Okay, so a few more words over here. So just to kind of add on. Um, so when we see a differential equation, abbreviated DE, of this form, of the form, your derivative is equal to a multiple of your function, we know that we get either exponential growth or exponential decay. Specifically, that E looks terrible, sorry. Specifically, if A is positive, you're going to get exponential growth because this population is going to get larger and larger if A is a positive, positive? Yeah, positive. If A is a positive number. and you're going to get exponential decay if A is negative. So if A is greater than 0, you're going to get growth. And if A is less than 0, you're going to get decay. Okay, we're going to come back to that idea in a little bit, but just hold on to it for now. So we're not going to make the analog right now because we need something else first. So I need to drink a water. I should pause actually. Are there any questions about this before we start talking about matrices for a little while? All right, cool. Also, for those of you on Zoom, I know people have asked questions in the chat before and I've totally missed them. If you ask a question in the chat and I don't see it after like a minute or two, please, please, please do feel free to unmute yourself and just say, hey, James, I asked you a question in the chat because I will address it, but I'm rarely looking at where the chat pops up. So don't feel dismayed if I missed your question before. All right, some more review from 17b. We're going to find the eigenvalues and eigenvectors of the following 2 by 2 matrix. Capital A equal to -1, 2, -3, 4. I'm sorry, I can't quite see all of that. I feel like there's something else I wanted to say here. I guess not. We should only be, so at this point for eigenvalues, eigenvectors, we're only ever dealing with 2 by 2 matrices, nothing larger. I know in 17b you might have seen different size matrices back then. This class only 2 by 2s, which are relatively not too bad. So first, whenever you're finding eigenvalues and eigenvectors, you kind of have to find the eigenvalues first. You can't really find the eigenvectors without knowing the eigenvalues. So to find the eigenvalues, we solve this equation. We're going to solve the determinant of A minus lambda times the identity matrix equal to 0. Let's write out what that is. So we're going to take the determinant of our matrix A, which is -1, 2, -3, 4, minus the eigenvalues that we're trying to solve for, which we call lambda, multiplied by the identity matrix, which is the n by n matrix, in this case, the 2 by 2 matrix, with 1s on the diagonal and 0s everywhere else. As a reminder, the identity matrix, where you have 1s on the diagonal and 0s everywhere else, the identity matrix is kind of like the number 1, in that if you multiply a matrix by the identity matrix, you get the same matrix back. So I'm not going to do it right now, but if you multiply this matrix by that matrix, you would end up getting this matrix back. Just like if you multiplied 5 by the number 1, you would get 5 back. So this matrix is kind of like the number 1 for matrices, multiplicatively at least. All right, let's finish this off. Well, let's continue on here. So really, you don't want to write all this down here. What you want to skip to is say, okay, well, if I'm ever subtracting lambda times the identity matrix, I'm really just going to be subtracting lambda in each of the diagonal spots. So we're going to rewrite this as the determinant of, let's see, -1 minus lambda in the first spot, in the first row, first column, and then 2 minus 0, and then -3 minus 0, and then 4 minus lambda times 1. So I would always recommend skipping this first step of writing determinant of your matrix minus lambda times the identity and just saying, yeah, I know I'm going to subtract lambda in the upper left corner and the lower right corner. That's always how it's going to work. Now, the determinant of a 2 by 2 matrix, in case you've forgotten, the determinant of A, B, C, D is always A times D minus B times C. Or I'll usually say the product of the diagonal entries minus the product of the off-diagonal entries. In this case, it's going to be -1 minus lambda times 4 minus lambda minus 2 times -3 equal to 0. For 2 by 2 matrices, this should always result in a quadratic equation. So I'm going to multiply this out. I'm going to have -1 times 4, -1 times negative lambda, negative lambda times 4, and then negative lambda times negative lambda is lambda squared, minus 2 times -3 is +6. I should rewrite this so it looks nicer. I've got lambda squared minus 4 lambda. Sorry, minus 3 lambda, because lambda minus 4 lambda is minus 3 lambda. Ugh, terrible. And then minus 4 plus 6 is plus 2. And some of the times this will factor. Some of the times this won't factor, and you'll have to use the quadratic formula. For sure. Like you are going to have to use the quadratic formula some of the time to find these eigenvalues. No doubt about it. Here are the factors. You're going to get lambda minus 1 times lambda minus 2 equal to 0. So our eigenvalues are going to, I'm going to say, are lambda 1 equal to 1 and lambda 2 equal to 2. Usually we do give our eigenvalues separate names, like we call one of them lambda 1 and one of them lambda 2, just so we can distinguish between which eigenvalue goes with which eigenvector. It's typical to call lambda 1 the bigger one, but I didn't do that here because I felt like it would be confusing to say that lambda 1 was equal to 2 and lambda 2 was equal to 1. That seems like it'd be weird to do. It also doesn't really matter. You can call lambda 1 whichever one you want. It's just pretty typical. You'll see most people call lambda 1 the larger one. Let's see. What else do I want to say here? Oh, yeah. I will point out there is another way to get to this equation, which you might have learned last quarter. This is a perfectly fine way of doing it, but I will also tell you that you can, let me try not to squeeze this in here, even though I really want to. So just so you're aware, another way to find the eigenvalues, the lambdas, for this matrix for A equal to -1, 2, -3, 4 is using the trace, which we usually use the Greek letter tau for, and the determinant, which we usually use the Greek letter capital delta, which is just a triangle for. So the trace is the sum of the diagonal entries. So the trace in this problem is -1 plus 4, which is 3. And the determinant is, as usual, the product of the diagonals minus the product of the off diagonals. So it's -1 times 4 minus 2 times -3, which is -4 plus 6, which is positive 2. And then how this always ends up working is the equation just becomes lambda squared minus the trace times lambda plus the determinant equals 0. So in this case, we would get the equation lambda squared minus the trace, which is 3, times lambda plus the determinant, which is 2, equal to 0. Same equation. It's just a different way of getting there. I don't usually do it that way, but it is somewhat useful. Yeah. Two other things I'll say because I think they're worthwhile. This is just something that's kind of neat. But yeah. I'll just say so. Note, and this is always true, the eigenvalues, lambda 1 plus lambda 2, add up to the trace. And they do. Our eigenvalues were 1 and 2, and 1 plus 2 is 3. And the eigenvalues multiply to the value of the determinant. And they do. 1 times 2 is 2. That's not something you need to know really, but I think it's just it's neat to know. It's worth knowing, and it kind of helps us see a few things later on. So keep that in my back pocket. But again, don't worry too much about this. All right, so we found the eigenvalues. Now we can start finding the associated eigenvectors. And there's a couple of different ways people do this. Did your instructor talk about finding eigenvectors in class yesterday? No. Okay. So I'll show you both ways of doing it. I don't think Tim is very particular, but occasionally some instructors are super particular about the way in which you find these eigenvalues. So I'm going to show you both ways one way for one eigenvalue, one way for the other way. Here's how I like to do it. So I'll remind you, how do I want to write this? Let me think for a second here. Yeah. So to find the eigenvectors, let me kind of section this off here. To find the eigenvectors, we're going to use the definition which is the following, that your matrix A multiplied by your eigenvector should equal lambda, your eigenvalue, times your eigenvector. Here's what this really means. To be an eigenvector of a matrix, what that means is that when you multiply the matrix by the eigenvector, the result still points in the same direction. You're just going to end up getting a multiple of that vector. I know it's been a while since we've talked about this, but when you so in fact, I'm going to do something else. So we're going to move away from this for just a minute, just so I can remind you of what's going on here. So here's a totally different example. I'm going to make up something in my head here real quick that's going to work, but let's not get it. So real quickly, if we look at a different matrix, let's call it B equal to, sorry, I have to think of a matrix that's going to work out. I'll think of something easy. Sure. B equal to, yeah, let's make it 2, 3, 0, -1. And in fact, this one actually shows something nice as well. Here, I made up something really easy by putting a 0 there or there. This matrix, when you have a 0 in the lower right corner or the upper left corner, or I would say this matrix is upper triangular because everything below the main diagonal is 0. If your matrix is upper triangular, the eigenvalues are just going to be whatever's on the diagonal. We're going to come back to that. Don't worry, that example's coming back, but let me just show you real quick here. If I want to find the eigenvalues, the determinant, now check this out. Here's the work I would actually want to show. The determinant of B minus lambda I, I'm just going to jump straight to saying it's the determinant of 2 minus lambda, 3, 0, -1 minus lambda. We just automatically subtract lambda from the diagonal spots. And then we do the usual thing. We multiply those together. So we get 2 minus lambda times -1 minus lambda minus 3 times 0. We want that to be equal to 0. Here's where you have to be aware of what's going on. Don't make more work for yourself. Don't multiply this out. Because this times this minus 0, it's already factored for you. You've already done the factoring without doing anything. This is 2 minus lambda times -1 minus lambda minus 0 equals 0. So it's really, really easy to see that the eigenvalues are going to be, oh yeah, I'm going to get lambda equal to 2 and lambda equal to -1. It's a 1. It's a -1. So if your matrix is upper triangular like this, or lower triangular, where you have a 0 up there, the diagonal entries are always going to be your eigenvalues. Okay, so now I'm just going to tell you what an eigenvector is. In fact, no, I'm actually going to start with a not eigenvector. So let's just make up some random vector. So let's look at this vector v equal to, I don't know, 1, 4. If you multiply this matrix by this vector, b times v, which is 2, 3, 0, -1, times the vector 1, 4, we end up getting, let's see, 2 times 1 plus 3 times 4, which is 2 plus 12, which is 14, and 0 times 1 plus -1 times 4. And what I want to point out is this resulting vector, this product of the matrix and this vector, this is not equal to a multiple of our original vector. These vectors point in very different directions. The vector v up over 1 and up 4 points like that way. And b times v, which is over 14 and down 4, points vaguely in this direction. All this just to say that typically, when you multiply a matrix by a vector, the resulting vector usually doesn't point in the same direction. Unless it's an eigenvector. What makes eigenvectors special is that when you multiply the matrix by the eigenvector, the resulting vector does point in the same direction. So here, one of the easy ones is, now I have to make sure I know what it is. Yep. That should work. Yeah. So one of the eigenvectors, let's say this is lambda 2 here, this is lambda 1 here. One of the eigenvectors is going to be V2 is the vector 1, 0. Because if you multiply this matrix by that vector, B times V2 is equal to 2, 3, 0, negative 1 times 1, 0. And we end up getting 2 times 1 plus 3 times 0, which is 2, and 0 times 1 plus negative 1 times 0, which is 0. And this is exactly 2 times the vector we started with. So in this special case, when you multiply the matrix by the vector, you ended up getting a multiple of the vector. And the multiple is always going to be the eigenvalue that goes with that the eigenvector. The other, sure, let me see. Trying to think what the other eigenvector is real quickly without like doing too much work here. I don't know what the other eigenvector is. I'd have to work to find it. I don't really want to do that work. But that's not really the point. The point here is that this is what this all means. Okay, so let's go back to the example we were working on. That's why you get to use this equation to find your eigenvectors. Because really, 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 we want the matrix times the eigenvector to equal a vector that points in the same direction, aka a multiple of the eigenvector. I should expand that what I said just a little bit. It can point in the same direction or in the opposite direction if it's a negative multiple, right? That's okay too, as long as it's essentially on the same line that the eigenvector would be on. So that's how we're going to find the eigenvectors. At least that's how I prefer to find the eigenvector. So we're going to take our matrix, negative 1, 2, negative 3, 4. The eigenvector is the thing that we don't know. We're trying to find it. So let's go ahead. Sorry, I should back up a second. We should have to pick which eigenvalue we're using first. And our eigenvalues were 1 and 2. So let's start with 1. So for lambda 1 equal to 1, we're finding our matrix times the eigenvector we don't know, which I usually like to call the vector xy, equal to lambda, which is 1, times the vector xy. Right, so the v thing here, the eigenvector, we don't know what it is. We're trying to find it. All right, here's how this usually plays out. This over here, this equation is really two equations in one. It's negative, I should point to this equation is two equations in one. The first equation is negative 1 times x plus 2 times y equals 1 times x. And what I really want to say is you almost only ever need one of the equations to find the eigenvector. I'm going to write down the other equation so you can see it, but we don't really need it. The other equation is negative 3 times x plus 4 times y equals 1 times y. In most instances, both of these equations will give you the same relationship between x and y. So if I isolate y here, I get 2y equal to 2x. I get y equal to x. If I isolate y here, I get I'm going to get 3y on the left equal to 3x on the right. I get the same relationship, y equal to x. All that to say, when you're finding the eigenvectors this way, you typically just need to look at one of the equations one of these two equations that this matrix equation gives you. So here's the relationship between x and y. So what's my eigenvector? Well, my eigenvector is whatever x is, whatever y is. So you have to just pick a number. There's one choice you are not allowed to make. The eigenvector cannot be the 0 vector. You can have 0 in one spot and something else in the other spot, like we had in that previous example we just did, but you can't have the vector 0, 0. So I'm gonna make it real clear over here. V can never be 0, 0. And the reason why is because if your eigenvector was 0, 0, your eigenvalue could be anything. The matrix times 0, 0 is always going to give you 0, 0. Doesn't matter what you have over here. Yeah. Well, so in this case, you're right. Neither of them could be 0. So pick any other number. Usually the choices we make are the choices that make x and y the smallest possible integers. So I would pick x equal to 1, and then y would also have to be 1. So here, one way of writing the eigenvector is that v1 is equal to 1, 1. But this is not the only possible choice. There are literally an infinite number of other choices that are correct. You could pick 2, 2. You could pick -3, -3. You could pick -5, -5, and all of us would be correct. Or in other words, any non-zero multiple of an eigenvector is also an eigenvector for that same eigenvalue. We try to make kind of standard choices by picking the values of x and y that are the smallest possible integers, but sometimes people make different choices, and that's okay. You'll still both be correct. So this is what we're going to pick here, but just be aware, any multiple of an eigenvector, any non-zero multiple of an eigenvector is also an eigenvector for that same eigenvalue. It especially comes up when one of the values is negative. Like if my eigenvector was 2, -1, I might pick 2, -1. You might pick -2, +1, and we both be totally right. Let's find the other eigenvector for the other eigenvalue. Oops, oops, you're in the way. I guess you'll go over here. Sure. Yeah. I'm trying to think of where I'm gonna put this piece of paper later. I guess you can go in the middle here. Okay. So for the second eigenvalue, we're going to do the exact same thing. We're going to write, no, we're not. Because I was going to do it the other way. So actually, I'll show you both ways here because I think both ways work. So I would normally just do this the same exact way. I would say, take your matrix, -1, 2, -3, 4, multiply it by your eigenvector that you're looking for, and it's now going to equal 2 times the eigenvector that you're looking for. And again, I would just use one of the two equations, usually the first one. So -1 times x plus 2 times y equals 2 times x. And then I usually isolate y. So I'm going to get 2y equal to 3x. And honestly, I would generally stop here. Although you can go one step further and say y equal to 3 over 2 times x. What do you think might be the nicest possible choice I can make for x here? It's going to make it so I don't get fractions. Right, I'm going to make x equal to 2. So one potential choice for my eigenvector here is x equal to 2, and then y will have to be 3. But some people like to say that x is 1. So another possible choice would be if x is 1, then y is going to be 3 over 2. Some people are just very much into always picking x equal to 1 if they can, and then y being whatever it is. Both choices are correct. Here's what I really want to point out, though. I wouldn't go, well, I would. So I'll say two things. This equation is useful, y equal to 3 over 2x, because when we start graphing these phase planes with all of your direction field vectors, this equation of this line is actually something that usually is useful to know. But this is really nice because if you stop here, there's a really, really easy way of knowing what to pick for x and y. Let x be the multiple of y and let y be the multiple of x. If x is 2 and y is 3, 2 times 3 equals 3 times 2, and it always works. So if you get to this stage here, pick x equal to the coefficient of y equal to the coefficient of x. That will always work. So I like doing it that way. But I said there was another way to do this, and I should show it to you because, again, your instructor might really, really want you to do it this other way. I don't think Tim does, but there was someone last quarter who was really like, no, you should do it this other way, not the way that I'm doing it here. So here's the other way you could do it. So again, this was trying to solve the equation a times your unknown eigenvector equal to lambda times your unknown eigenvector. But you could also try to solve it by solving A minus lambda I times your unknown eigenvector equal to the zero vector. And really, all you're doing to get from this equation to that equation is you're subtracting lambda times v from both sides, and then you're kind of factoring out the v, but you can't really factor out the v and have a lambda there because a minus lambda doesn't make sense because a is a matrix and lambda is a number. So that's why you have to throw in that 2 by 2 matrix either to make it work. Let me show you what this looks like. So here we're going to have the equation a, so -1, 2, -3, 4, minus our eigenvalue, lambda, times the 2 by 2 identity matrix, multiplied by the unknown eigenvector we're looking for, equal to the zero vector. Okay, and again, you really should never actually write it this way. What you should typically do is to say, hey, I know I'm going to be subtracting whatever my eigenvalue is, in this case 2, from each of the diagonal entries. So what I really want to write is -1 minus 2, 2 minus 0, -3 minus 0, 4 minus 2. And what almost always happens when you do it this way is both rows of the matrix look exactly the same or are multiples of each other. And in either case, you're going to get the same equation here. My equation is going to be -3 times x plus 2 times y equal to 0, which is the same equation that we got over here. We're still getting 2y equal to 3x, which means we're still getting the eigenvector of x equal to 2 and y equal to 3. So either one of these ways is totally fine to do it. I will say this first way of doing it, I prefer. And it's what I default to just because I am always thinking of it as, oh yeah, the matrix times the vector is a multiple of the vector, or the matrix times the vector points in the same direction as the original vector. But this works really nicely if your eigenvalue is a nice integer or a nice fraction. It's less nice if your eigenvalue is irrational, or even worse, complex, which they will be. We are going to encounter complex eigenvalues, unless Tim really cuts out like a big section of the class, which I don't think he's going to do. So count on seeing imaginary numbers in your very near future. Yeah, I know, but we're going to just have to deal with it. So when your eigenvalues are not so nice, this way actually is a little bit easier to deal with. So you might, if you're unsure which way you want to go here, you might just start doing it this way because this way kind of works better in all situations than this way does. So maybe I should do it this way too. Ugh, I don't like doing it this way though. Okay. Anyway, I'll have to deal with that on my own, I guess. So we're going to now kind of take a broad review for a minute and go back and kind of incorporate the stuff we talked about at the beginning of class today, which is the solution to the differential equation where the rate of growth is a multiple of the population size. We're going to try to now kind of incorporate that into what we're doing here. So yeah, let's use a new piece of paper here. So here is the example we want to start with. Let's see how this all relates to 17C. So we're going to do the following. We're going to yeah. You should let me know. So I should ask you, actually, he talked about this a little bit in class yesterday, right? Some of this, not all of it, maybe.
There's some like discussion.
Okay. So I was gonna ask, is he typically using X and Y, or is he using like X1 and X2?
Usually C1 and C2.
Okay. All right. Okay. So we'll go back and forth. So we're gonna let X1 of T equal the population of a predator. Think wolves at time t. And X2 of t is going to be the population of prey. Think like deer at time t. So then dx1 dt is the rate of growth or the growth rate of our predator. And so how the population is either increasing or decreasing as time goes on. And dx2 dt is equal to the growth rate of the population of deer, of the prey. I should really say predator population, prey population. Some sort of basic level, it would make sense that these two things would depend on each other, right? If you have lots of prey, then the growth rate of the predator is probably going to increase because, right, there's more prey for them to eat, so they're going to grow. But also then, as there are more wolves, well, the more wolves there are, the less resources there are for each of them. So actually having more wolves might make their population decline because there is less. In a similar sort of way, right, if there's lots of wolves, the deer are going to get killed faster. So they're going to decline. But if there's lots of deer, they're going to make more deer. So they're also going to grow. So I realize I'm kind of making this very basic. And again, I'm not here to talk about the biology, really. I'm here to talk about the math. So that's kind of the very, very basic example of how these things are interdependent. Here's the equation that we're going to say is the relationship between their rates of growth and their population sizes. So we're going to say that dx1 dt, the growth rate of the predator population is going to be -1 times x1 plus 2 times x2. So again, having more wolves is going to make the growth rate decrease or go down, but having more prey is going to make the growth rate of the wolves increase because there's more for them to eat. And then we're going to say that dx2 dt, the growth rate of the deer population or the prey population, is going to be negative, what was it there? 3 times x1 plus 4 times x2. So again, right, the growth rate of the sheep is going to go down if there's lots of wolves, right? If x1 is big, the rate of change of the deer population is going to be smaller because the wolves are going to eat them. But if there's more sheep, right, they're also going to, I keep saying sheep, I mean sheep, deer, whatever, they're prey. If there's more prey, they're going to make more of themselves because, they procreate. So, yeah. And then we're going to also have some initial populations. We're going to say that at time zero, x1 of time zero, x1 of zero, or the number of wolves at time zero is 2, or like maybe we're talking about wolves in the thousands. It's 2,000 wolves. And the number of deer at time zero is 4,000 or 4. Okay. Um, Something to think about as well. If we started off with 0 prey, so if that was 0, what would happen to the wolf population? Well, it would decline, right? Because their rate of growth would be the -1 times the number of wolves there were. Or our constant multiple would be negative. In a similar way, if there were no wolves, the deer population would grow. Okay. All right. So now here's the deal. This equation can be written as a matrix. This equation is this, we can write this side as a vector. This is dx1 dt, dx2 dt. That's the first and second component of this 2 by 1 vector. It's equal to the coefficient matrix, -1, 2, -3, 4, multiplied by the variable matrix, x1 of t, x2 of t. That is the same equation, or I should say, it's the same system of equations. Just written as vectors and matrices. This is written as vectors. This is the vector dx with an arrow over it, dt. It's the derivative vector equal to the coefficient matrix A times the variable vector x, or x of t. Hey, that equation looks kind of familiar. It kind of looks like we have the derivative is a constant multiple of your variable or your function, kind of like we started off with class today. And so we might expect, let me go down here. So for this equation, dx dt equal to a times x, we might expect the solution to look something like x equal to a constant times e to the a times t, right? Just like d regular x dt equal to a constant times regular x had x of t equal to c e to the regular a times t as a solution. But there's a problem. I forgot the problem. I forgot the problem with lights. Sorry, maybe that's a little easier to see now. Not that it was impossible before, but yeah. So the problem is e to the power of a matrix isn't something we can really deal with, right? This a here, that's the 2 by 2 matrix, -1, 2, -3, 4, or whatever matrix we're dealing with. Whereas this a here is just a regular number. That makes sense. That, not so much. So what do? We can't really calculate c e to the at. So the idea is, so instead, we replace the matrix A with its eigenvalues and eigenvectors. Because the eigenvalues are regular numbers. You can totally say e to the something times t. So instead of x equal to c e to the matrix times t, that's not going to do it for us. We're going to do this instead. Our solution is going to be the x, or x of t, I guess. So here's the actual way we write the solution. Instead of c e to the matrix times t, it's going to be c1 e to the lambda 1 times t times the first eigenvector plus the same thing but with twos. c2 e to the lambda 2 times t times the second eigenvector. And that is definitely a thing you want to memorize. This is the general solution to dx dt equal to a times x. It's pretty easy to remember because really it's just the same thing twice. It's a constant times e to the eigenvalue times t times the associated eigenvector, and then you do it again, but it's twos instead of ones as your subscripts. Cool. Well, good news. We already found the eigenvalues and eigenvectors for this matrix, right? It's literally, right, the matrix here, -1, 2, -3, 4 is the matrix we've already been working with today. So let's go ahead and actually write the solution for the particular system we're looking at. I'll write it again. So for dx dt equal to the matrix A, which is, where'd you go? -1, 2, -3, 4 times the vector x, the solution is x of t equal to, we don't know what C1 and C2 are yet. C1 e to the lambda 1 was 1 times t, and V1 was the vector associated with lambda 1, which was, good question. Let's look back at our notes and see. It was 1, 1 plus C2 times e to the 2 times t times the eigenvector associated with lambda equal to 2, which was 2, 3. And this is our general solution. And the reason it's general is because it's the solution without any given initial conditions. We're just saying for this system, if you don't know where you're starting, this is the solution for whatever. But if we have initial conditions, we can solve for the constants C1 and C2. And we do. Our initial conditions were x1 of 0 equal to 2 and x2 of 0 equal to 4. So we're going to rewrite this. So check this out because I feel like this is a place where people often get a little bit confused. I didn't write it, but this is a vector, right? X with an arrow over it of t, that's really the vector, right? This here, this is really x1 of t in the first component, x2 of t in the second component. So when I write x of t equal to 0, I'm really writing the vector x1 of 0, x2 of 0, which is equal to, in this particular example, 2, 4. But then it's going to equal this whole other side with t equal to 0 plugged in. So it's going to be c1 e to the 0 times 1, 1, plus c2 e to the 2 times 0 is still 0, times 2, 3. And e to the 0 is 1. So really what we end up with is C1 times 1, 1 plus C2 times 2, 3. There's a couple ways of solving for C1 and C2. I'm going to show you kind of the most straightforward way. So really I have two equations. I have, let's write this down again. I have 2, 4 equal to C1 times 1, 1 plus C2 times 2, 3. In fact, I should point out, I think it's really important for you to remember that whenever you write something like this, you're writing down two equations at once. My first equation is the top row. It's 2 equal to C1 times 1 plus C2 times 2. If you wanted to, you could actually distribute the C1 into this vector and the C2 into that vector, but people don't usually do that. Not because you can't, just because it's not common practice. In a similar way, I can say that 4 is equal to C1 times 1 plus C2 times 3. And then you can solve this system of two equations and two unknowns in whatever way you like. I happen to notice here that C1 in each equation has the same coefficient. So if we subtract the second equation from the first equation, we can get 2 minus 4 is negative 2. C1 minus C1 is 0. 2C2 minus 3C2 is negative C2. And then we're going to get C2 equal to positive 2. And then plug that back into either one of these equations. If C2 is 2, then 2 is equal to C1 plus 4. And subtracting 4, we get C1 equal to negative 2. So our particular solution, and here I should have written the general solution. Sorry about that. But the particular solution for this whole situation, the particular solution is the same solution just with the C1 and C2 values plugged in. So it's going to be x of t equal to 2 times e to the t times the vector 1, 1 minus 2 times e to the 2t times the vector 2, 3. Well, that's a lot. So to kind of sum up what we said so far, when you're given a system of linear differential equations where you have the derivative of x1 is equal to a multiple of x1 plus a multiple of x2, and the derivative of x2 is equal to a multiple of x1 plus a multiple of x2. The way you solve that system of equations, of linear differential equations, is by writing down the 2 by 2 matrix, finding the eigenvalues, finding the eigenvectors, writing this general solution, and then if you have initial conditions, finding C1 and C2 and writing this particular solution. It's kind of a lot to do for kind of one question, but it is a process that's pretty easy to do once you've done it a few times. So I really, really can't stress enough, practicing doing this a number of times is kind of vital to being good at it. And you are going to want to be good at it because you are going to have to do it. Okay, so we're not quite done with this problem, but are the questions? I did switch the C1 and C2. Apologies. It should have been -2 times e to the t times 1 plus 2 times e to the 2t times 2 3. Thank you. Good catch. Oof. So, I don't know. You guys are using web work, right? So sometimes on web work, you'll ask you to find this, they'll ask you to write the solution, and they'll ask you to write like what the X1 solution is and what the X2 solution is. And just like we've been doing so far, X1 is just whatever's in the top row, and X2 is just whatever's in the second row. So writing this again here, we know that X of t is really the vector with the function X1 of t. X1 doesn't get a little arrow over it. It's not a vector. Let me draw it again. X of t, the vector, consists of the function x1 of t and the function x2 of t as its components. And that's equal to all this. -2 e to the t times 1, 1 plus 2 e to the 2t times 2, 3. So what that means for us is that x1 is just the top row stuff. So x1 of t is -2 e to the t times 1 plus 2 e to the 2t times 2. Or written like in a more normal way, it's -2 e to the t plus 4 e to the 2t. In a similar way, x2 of t is equal to -2 e to the t times 1 plus 2 e to the 2t times 3, which is going to be 6 e to the 2t. And sometimes we like to ask, so like, what does this mean the populations are going to do as time goes on? So as time passes, do these populations grow, die out, reach some sort of equilibrium? Well, those last two questions are actually the same question because I'll say this without kind of, or with emphasis here, for a linear system of differential equations like this. And again, I want to be super clear. What I mean is when your system looks like the derivative of x1 is equal to a multiple of x1 plus a multiple of x2, and you have nothing else. And similarly, the rate of change of x2 or the growth rate of x2 or the derivative of x2 is a multiple of x1 plus a multiple of x2. The only equilibrium is 0, 0. The only way that, well, when we say equilibrium, what do we mean? We mean we've reached a place where the population is steady, is not changing, where the rate of growth is 0. The only way that both of these equations can equal 0 at the same time is if x1 and x2 are both 0. Because a times 0 plus b times 0 is 0, and t times 0 plus d times, unless they happen to be like parallel lines, but they're not usually parallel lines. So, not to be grim, but in this example, everything dying is the equilibrium. Because if there's no deer and there's no wolves, the population just stays at 0. But that's not what's going to happen here. Because if we take the limit as t goes to infinity of x1, let's see what happens. We have limit as t goes to infinity of x1 of t is equal to the limit as t goes to infinity of, let's see, we've got -2 e to the t plus 4 e to the 2t. So we have this thing here going to negative infinity, and this thing here going to positive infinity. And negative infinity plus infinity is an indeterminate form, but hopefully you can look at this and see which of those infinities is actually growing bigger. It's the e to the 2t, right? It gets much, much larger. If that's not super clear, one way you can deal with this and actually make it work is you could factor out an e to the t from both pieces and write it as the limit as t goes to infinity of e to the t times -2 plus 4e to the t. And then you can say, oh yeah, I've got something going to infinity times something going to infinity. So this does go to infinity, meaning you get infinite wolves. Okay, so maybe these models don't take into account a lot of environmental factors, but that's not the point. The point is that over some small amount of time, you can see what's happening. Similarly, if you take the limit as t goes to infinity of x2 of t, the prey, you're going to get a similar result. It's going to be the limit as t goes to infinity of -2 e to the t plus 6 e to the 2t. And again, this e to the 2t is the bigger power it's going to overcome. So that's going to go to infinity. Yeah. There's something else to say here, but I'm going to wait on that for a minute. Okay, so something you might, and I think, oh, let me actually, let's take a look here. So I believe I have linked this in Canvas, but let me make sure. I have a couple graphing links here, which I think are worth you using occasionally to see what these things look like. But let me make sure that they're in Canvas before I just say that they're there. Let's see. So Co-17C. Come on, Canvas. Yeah, cool. There we go. So if you look over here, you look in Canvas below like the recordings, the useful links. No, below the useful links, the links are graphing. 3D, not the 3D, the graphing the phase plane. So these two links here are what I like to use. So that one's fine. This one is probably less like this one's easier to use, but doesn't really give you as much. And the other one is a little bit less easy to use, but I feel like it gives you a little bit more. Here's what I mean by that. So let's go to the other one here. Sure. Cool. Yeah, this one looks more. So here's how we can graph the phase plane of this system of linear differential equations. So my dx, so you do have to use x and y in this one instead of x1 and x2. Okay, fine, that's fine. So our dx dt was, I forget what it was. It was -x plus 2y, yeah. So for this one, any multiple of x or y, you have to use the asterisk symbol for multiplication. So it's -1 times x, but -x is fine, plus 2 times y. And my other one here was -3 times x plus 4 times y. And then you graph the phase plane. And that's what it looks like. So meaning if you start, say, at the initial condition of, why am I looking up there? I can look over here. Of x is 2 and y is 4, and you can trace the path. That's the way it goes. So if you start at 2, 4, which is right here, you just shoot off in that direction towards x being infinitely large and y being infinitely large. And if you had a different initial condition, you would end up with a different trajectory. If you started over here, well, it doesn't really make sense to start with negative amounts of things, right? But if you started with, like, say, all deer, so if you had, oh my gosh, I keep trying, yeah, I keep trying to look over there. If you started with, say, like 0 wolves and let's say 3 deer, what's going to happen? I have to click a button. Interesting. So, well, maybe the context doesn't make a whole lot of sense sometimes. Anyway, but if you start this initial condition, you're still going to shoot off that way. So, okay, I feel like there's maybe some explaining I have to do about that that I have to think about. But essentially, the idea is you can start at any point and just kind of follow the way the arrows point you to see how the populations are growing in concert. Oh, and there was this, so the other graphing utility I feel like is kind of neater in that it shows you some cool stuff. So manipulating it's a little bit harder, but if you click here and then you want a system of differential equations, and then we're going to say it was -x plus 2y. I don't think you need the asterisks here. And this other one was, oh, geez, it does that all the time though. You have to be like, and then the other one was -3x plus 4y. And then hit the little gear thing over here so you can change the window. So you get like -10 to 10. So hopefully, I feel like okay. So if we start at the same initial condition, you can even do that there. So if I start at say like 2 comma 4, it has the same sort of thing. This one feels like it's a little stretched widthwise, but okay. What I do really like about this one is if you click on the time plot, it shows you the x and y function. So this x function here is exactly our negative 2e to the t plus 4e to the 2t. And our y function there in blue is exactly our negative 2e to the t plus 6e to the 2t. And if you look at the initial conditions, you're exactly getting at time 0 a y value of 4 and an x value of 2. So useful to see what's going on, I think. All right. Yeah.
Negative x plus 2y.
Uh-huh. So here's the thing. I am graphing the system so this graph is the solution or all solutions really to that system of differential equations. So what's not being displayed here is all the work that we just did to find x equal to negative 2e to the t plus 2e to the 2t and y equal to negative 2e to the t plus 6e to the 2t. We did all that. Those solutions are here, they're just not displayed. But right, we're plugging in the initial thing and saying instead of us doing all the work, we're letting this program do all the work, and it spits out both the phase plane, which kind of shows you what any solution kind of looks like, depending on where you're starting at, what your initial condition is, as well as for that initial condition, you can actually see what the individual solutions graphs would look like. So these two graphs here, even though it'd be nice if they told us what like if they wrote the equations of the graphs, they're not. But if you go over to like just to kind of show you, if you look over at Desmos here, if you graph the first one, sure. Trying to think about, I'll just use y and x. So y equal to where'd you go here? Negative 2e to the x plus 2e to the 2x. Starting at 0 shouldn't get me 0. Did I make a mistake? I did. No, you're right. It should be 4. Thank you. Good call. That should be 4, not 2. And then if you cut off the parts where x is negative, right, there's essentially the same portion of the graph. Now it looks way steeper because of how my window is, but that right there is exactly the same graph as the blue one there. The blue one, the red one, the red one. And then I can graph the other one. Can I? That was a 6, I think, right? Yeah. There's the blue one. So there's your two graphs of the solutions. So you don't have to do all the work of graphing them or finding them to graph them. You can say, hey, cool, look, there they are right there. Right, with the specific initial conditions. Right. So again, if we picked different initial conditions, we would have found different constants C1 and C2, which would have meant we got different graphs. Okay. So let's see. What else do I want to say here? Oh yeah, I feel like I should say that because I feel like that's something Tim would want to ask about probably. Oh, there's a question. I see a hand on the oh my gosh, well Zoom. Does someone have a question on Zoom? So we're just going to write our limit as t goes to infinity. Oh, okay. It seems to be working now. At least I think it is. Okay. So anyway, sorry about that. I don't know what's going on. Yeah. Okay. It says it's working now. Great. Okay, cool. Audio issues. Okay. So take this limit. I'm just going to use my solutions here. The solution for this one was negative 2 e to the t plus 4 e to the 2t. And the bottom one was negative 2 e to the t plus 6 e to the 2t. Okay, so how am I going to take that limit? Ugh. So we're going to do what we usually do. Usually, what you would have done in 17a, you're going to divide everything by the thing that's biggest or growing the fastest, which in this case is it e to the t or e to the 2t? Right. So don't worry, you're not going to have to usually do this. So if we divide everything by e to the 2t, we're going to get the limit as t goes to infinity of negative 2 e to the t divided by e to the 2t is going to be divided by e to the t plus 4 e to the 2t divided by, I should write, I'm being a little bit lazy here. Let me show my work. I get negative 2 e to the t over e to the t. I get 4 e to the 2t over e to the t, 2t. I'm dividing by e to the 2t, which is what you all said. Same deal on the bottom, dividing by e to the 2t, and 6 e to the 2t divided by e to the 2t. And then if we simplify, we get negative 2 over e to the t plus 4. On the bottom, we get negative 2 over e to the t plus 6. These parts go to 0. And so we're left with 4 over 6, which reduces to 2/3. I'll remind you, and this is not a coincidence, that the eigenvector associated with the larger eigenvalue, lambda 2 equal to 2, is V2 equal to 2, 3. It's not a coincidence. Here's what's true. As long as one of the eigenvalues is positive, whichever eigenvalue is bigger, that eigenvector shows you the proportion. So if lambda 1 is bigger than lambda 2, and lambda 1 is also positive, then the eigenvector going with lambda 1 shows the proportion that we settle to. And if both lambdas are negative, the populations die out. Let me emphasize that a little bit more. We'll do an example. We have time. No, do we have time? Maybe. Yeah, sure. Yeah, let's look at a real quick example here. Um, so one more thing I'll say here is that means overall the fraction of wolves in the population is 2/5, and the fraction of deer in the population is 3/5, or tending towards 3/5. So x1 of t tends towards 2/5 of the total because it's 2 divided by 2 plus 3, and x2 of t tends towards 3/5 of the total of deer and wolves. This doesn't always come up, but I feel like your instructor is someone who would ask this kind of question, so I felt like it was worthwhile. It's worthwhile anyway. Okay, how much more can I say here? Yeah, let's do one more example. I want to do. Sorry, this one. Nope, not that. Let's do that. Okay, sorry. All right, yeah. So let's say another example. Find. I'm looking for something here. Yeah, okay. There we go. So find the general solution for the system dx dt equal to negative 2x plus y, dy dt equal to 2x minus 3y. We probably won't finish this today. We might. So whenever you have this, you're always going to rewrite it, right? We're going to rewrite this as a matrix equation. Our derivative vector, which if you want, you could write as actually a vector instead of writing it as x1 over it. By the way, I'll point out this is actually one of the reasons we use x1 and x2 because it kind of feels weird to say that the vector is x where its components are x and y, but it's fine. And then we're going to say that's equal to my coefficient matrix, which is -2, 1, 2, -3, multiplied by the variables vector xy. And there's our matrix A. And instead of doing all the work, I'm just going to I'm going to tell you what the things are so we can get to the thing I want to say. But I do think it's worth your while to go back and do this work. So I'm going to tell you, but you should find so later do the work. It is good practice, and you should all practice this as much as you can to find the eigenvalues equal to -1 and -4, and the eigenvectors equal to 1, 1, and 1, -2. Again, I really think you would all be well served doing that on your own. Also, I'll point out the notes to this are posted on Grant's website. So if you want to like see the actual work after you have done it yourself, then you should feel free to go look. It's the one labeled graphing a sink. This is graphing a sink on Grant's notes. Graphing a sink. But then our general solution would look like this. Our solution is x of t as a vector equal to c1e to the -1 times t times v1 plus c2e to the -4 times t times v2. And the point I want to make here is that as t goes to infinity, both e to the -t and e to the -4t go to 0, right? E to the -t goes to 0, and e to the -4t also goes to 0. So as t goes to infinity, this whole thing is going to go to 0, 0. So this goes to 0, 0 as t goes to infinity. Meaning, if we're thinking of this as populations, both populations are going towards extinction, right? You're going to get 0 wolves and 0 deer if this is your model for growth. And that's why this is called a sink, because we see that in this direction field, in fact, we can actually see it in this direction field. If we were to graph this one instead, sure, I can use this one, where it's -2x plus y. And the other one is 2x minus 3y. So if you look at this, no matter where we start, we end up going in towards the origin. And so whatever initial conditions we had, we end up getting closer and closer to x being 0 and y being 0. So we're sinking in towards the origin instead of, what's the other one called? The other one's called like a source. So we'll talk more about the names and stuff later, but that's the reason why this is a sink is because both of our eigenvalues are negative, which results in, sorry, I'm closing the wrong thing here, which results in, right, this part going towards 0 as t goes to infinity, as does this part. So if both of your eigenvalues are negative, your whole populations both go smaller and smaller and smaller, getting closer and closer to 0. So in this case, 0, 0 is the equilibrium that well, I should say 0, 0 is always the equilibrium. It's just in this case, it's the stable equilibrium that we're moving towards instead of the unstable equilibrium that we're moving away from. All right, next week on Tuesday, we'll talk about more like kind of classifying what kinds of equilibria 0, 0 is, whether it's a stable node, an unstable node, a saddle, a spiral. Spirals are when you have imaginary eigenvalues, which are less fun to deal with, but you gotta deal with them. All right. See you all next week. Attendance. I forgot about the attendance. Please throw your name on the attendance sheet. Here's a pen if you need it. Put it right here.